Okay, thank you, Keijing, for your nice introduction, and good afternoon, good evening, everybody from a sunny and warm Milan. Today was a very spring hot day. Well, actually, the work that I'm going to present is part of a very large research project that I am coordinating, funded by the European Commission. And the name of the project is Resilience. Actually, we are going to produce and validate several UHPC mixes for different structural applications, even in very aggressive environments. Some of them were presented yesterday during the smart concrete session, and something during the Sunday session on UHPC application. This work today, which fits with the topic of the session, deals with the correlation between the rheological properties of high performance fiber reinforced composite with adapted rheology, which is actually UHPC, and very early age fracture properties. And is a collaboration between my colleagues, Professor Cremonesi and Dr. Lomonte, two master students of mine who graduated, our lab technician, and also a research group from Leibniz University in Hanover, led by Professor Michael Ice and his PhD student, Julian. Well, actually, we have also learned from previous presentation how in UHPC, fresh state performance and rheology, fiber dispersion and hardened state performance, and then structural performance are strictly correlated with a mutual interaction. And I put on the right-hand side of this slide some results we have been obtaining, I would say something like about 10 years ago, in which controlling the orientation of the fibers, you can have, this is exactly the same material, the same structure, simply testing it in a direction rather than in the other, you get a very different performance at the material and structural level. Then we wanted to see, is there any correlation between the rheology and the very early age performance? So actually, I would say that the motivation for this study came from some 3D printing applications we have been working with. For example, you have to print a filament which has to resist to forces during the printing, or you can print a formwork, and if you fill with concrete, hoop tensile stresses arise. And you want to know how fast can you go with this kind of applications. But also in precast applications, you may need to know how fast some properties develop because you want to speed up your process, your production. So what does very early age mean? Here we focused on the properties up to 2-3 hours after the end of the mixing. So we developed these tensile and shear fracture specimens. You can see there the measures are in centimeters, so they are quite compact. We developed like that because also we wanted to make this setup portable to different sites. And these are the molds. We equipped them with a load cell able to apply the load in displacement controls. And we use that for the tests here because we need a very sensitive equipment. We use a load cell with a maximum capacity of 60 kilograms and an accuracy of 1 gram. Whereas we use it the usual LVDTs that we use for our hardened state fracture test because we deemed that the accuracy was correct. So we worked with a UHPC mix we have been validating for quite some time, containing SEM1. Sorry, in the writing there is a misprint. The correct notation is in the table below. SEM1 52.5R, according to the European standard notation, use blast furnace slag, a water binder ratio equal to 0.18, compensated by quite high superplasticizer, and we use natural sand up to 2 millimeter maximum aggregate size. And we investigated, in this case, a reference mix with no fibers, the matrix, and 3 different fiber dosages equal to 40, 80, and 120 kilos. These are still microfibers, 20 millimeter long and with a diameter of 0.22 millimeters. So the aspect ratio is about 90. And these dosages correspond to 0.5, 1%, and 1.5% by volume. Well, here is a short movie. This is a tensile fracture test at about 2 hours. So we fill the mold, we poured the mix from one side, and you can see the fibers were very well aligned in the direction of the tensile force. And you can see how our test ended up with complete separation of the two specimen halves in two blocks. So here you have some results. This is the matrix at going clockwise from top left to bottom left. You have the first test at 1 hour where the response is still fluid. Before 1 hour, actually, we were not able to perform any test because the mix was really liquid and flew out of the mold. So you have at 1 hour, 1 hour and a half, 2 hours and 3 hours, and you can clearly see, you can clearly detect how the results of our test were able also to highlight some fluid to solid transition. And the same happens for the mix with 80 kilos. This is just an example, mix with 80 kilos per cubic meters of fibers. You can also see how, well, 80 kilos is surely still not strain hardening this material. These are direct tensile tests, but there is a significant post-peak toughness compared to the matrix. Well, we compared, we plot here the maximum tensile strength for the different dosages of fibers versus the time. So from 1 to 3 hours, you can see there is a clear increasing trend. And actually, you can see that there is some kind of translation in the slope also at 120 kg of fibers per cubic meters. An image of the plot. So then we went to shear fracture test. This is another movie. You can see that the shear fracture test starts with a clear one set of the diagonal cracks from the notch tips, and then you have the shearing off of the ligament cross section with complete separation of the two specimen halves. And also here you can detect, this is an example of the mix with 80 kilograms of fibers per cubic meter, or as is written here, 80 grams per liter. And you can see evolving from 1 hour up to, this case is 2 hours and a half. You go from a fluid to solid transition, and at a certain point we reach the maximum capacity of our load cell. On the top right, you have the same tests for the matrix, which remained, by the way, well below the load capacity of the cell. So there is also contribution of the fibers in controlling the crack propagation and also in governing the strength of the compressive strut that is formed in between the two inclined cracks that forms, as it can be seen here. Well, then we went for analyzing the fresh state performance. This is a movie of a slump flow test. We also developed a small, frame to keep a camera at 90 degrees, really filming vertically the slump flow test, and then we processed the movie, so we were able. We are performing some fluid state simulation, some computational fluid dynamic simulation. You can see how the slump flow versus time curve is evolved, but we also calculated as a preliminary assessment of the rheological properties evolution. We calculated the loss of slump. You can see that increasing, there is a common trend, but increasing dosage of the fibers, there is some change also in this curve. So there is an interaction between the fibers and the matrix in the governing the evolution of the rheological properties. What is interesting is that we tried as a first attempt to correlate the tensile strength of the fiber reinforced composites versus the loss of slump flow. And you can see here that the trend, there is a common trend between 0 and 40 kgs per cubic meter of fibers, and there is a significant jump when you go to 80 and 100. So this was also evident, even more evident for the shear stress, where the results for the reference mix and mix with 40 kilos per cubic meters of fibers are pretty quite the same, whereas you have an increase for 80 kilos and a further increase for 120 kilos. So we went, and this is part of the investigation which has been done by one of my students at Leibniz University in Hanover. We did some rheological investigation employing this Mars Hackett rheometer with load cell specifically studied for cement-based material. Actually, Professor Heist was the one who designed and patented this cell. And we detected, for example, that yield stress versus time and versus the fiber content. You see that up to 40 kilos of fibers per cubic meter with the time, there is almost no change, but there is a sudden jump between 1 hour and a half and 2 hours when you go to 80 kilos per cubic meters. With 120 kilos per cubic meters of fibers, the rheometer tests were actually quite difficult to be performed. Then, employing a protocol which was developed at the Northwestern University by Ray Ferrara, when I was there as Fulbright visiting scholar in 2006, she was completing her PhD, so I remember we worked in the lab together. And the rheometer protocol, we performed first an equilibrium loop, and then we redid the same protocol at regular intervals of 15 minutes up to 135 minutes. And then isolating the results between two significant shear strain rate values, superimposing the equilibrium loop and the successive descending branches, the area between these two curves is defined as specific rebuilding energy. Actually, it's an energy per unit volume and per unit time. So its dimensions are, Pascal second to -1. You can see here the results that I showed previously. These are for the reference matrix, for the reference mortar, so they are quite regular and very good results, but they become a little bit more dispersed as long as the content of the fibers increases. So there is a matter of characterizing properly the rheology for increasing dosages of fibers. But as a matter of fact, there is a clear trend. The blue line is the reference mix, the orange is with 40 kilos per cubic meters, and the green, sorry, is a little bit more dispersed, but is the trend for 80 kilos per cubic meter. And you can see as this energy increases with a regular trend with time. So what we did here, we plotted the mechanical properties of the mix, so the tensile strength versus this structural specific rebuilding energy. Obviously, these refer to the same time frame, but for the different mixes, you have different values. And you can see that there is a good trend. So clearly highlighting how this thixotropic structural rebuilding starts being responsible of the mechanical properties, both for tensile strength and for shear strength that we have been measuring with our device. So coming up to the conclusions, we have developed, designed, and validated this test setup and methodology to identify the tensile and shear fracture parameters of UHPC, basically during the fluid to solid transition stage. And we are completing this with penetration tests to identify compression strength evolution in order to be able also to build up a Kupfer domain and its evolution over time along these early age stages of the material. We have been validating a correlation also with the evolution of the rheological properties, and also to detect an evolution of the fiber matrix interaction and its role in both rheological and fracture properties. And with this, I thank you and all my team here that you can see in two pictures taken 1 year apart from each other, before and after this pandemic time, and thank you for your attention once again.
Thank you very much, Liberato, for the very interesting, very informative presentation. Not what I see.
Okay, Jane, can I unmute myself and ask a question?
Sure, go ahead.
Because we have to give Liberato some questions. First of all, sure. Presentation as usual. Liberato, this is the third day in a row I see you like after 11 o'clock your time, 12 o'clock.
Yeah. Well, this time is nice for me now because it's just 7:30, 7:45.
Question for you. Did you look at thixotropy over different periods of time? How did you handle the rest period between different times? Was it the same sample that was used?
Yeah.
Or the virgin sample every time?
Yeah, it's true. It was the same sample which stayed in the cup of the rheometer, let's say. So we sheared it, then have it rest, and then we re-sheared it and have it rest. Yeah, was it exactly the same sample?
Okay, thank you.
Thank
Great.
you.